So previously we have studied the armature winding design, and we have studied the wave winding and the lap winding. Uh, we were actually deducing the equation for the internal generated voltage. Before we do that, let's see the problems that are associated with commutation. So as already stated, the voltage in the armature winding is AC in nature. It's not a DC voltage or a DC current that's flowing in the armature winding. It's AC voltage generated and AC current flowing in the armature windings. But at the terminals of the terminals through the brushes, we basically obtain the DC voltage, and we feed the DC voltage to a DC machine. So this the process basically involves, there is a rectification and inversion process wherein your DC to AC and AC to DC conversion takes place, and this is done mechanically by the use of commutator and brush arrangement that we have seen so far. But this commutation process associated with DC machines is not fairly straightforward. There are some associated problems with the commutation process, and there are actually two main problems. One is known as the armature reaction, and second will be L di by dt voltages problem. Fine. So we have to discuss two important problems and how to mitigate these issues. The first one is the armature reaction. So what happens in a DC machine, if the magnetic field is connected to the power supply, say for example we take the case of a DC generator. The magnetic field will be produced by an external DC source, and the rotor will be turned by means of an external source of mechanical energy. So that means voltage will be induced in the rotor windings, and this is the windings that the voltage that is actually induced in the rotor windings will be AC in nature, and through normal process of commutation and brushes we can actually obtain the DC voltage. Now what happens is, if we connect a load to the armature, now since this is a DC generator, we'll start loading it. Once we load this DC machine, because of the loading effect, the current will actually start to flow through the armature windings, and the armature windings will therefore, because of the current flowing through the armature windings, it will produce a magnetic field of its own. Fine. So initially what you had is you have a we're talking about a DC generator. Now forget about the brush and commutator. There's a brush and commutator segment here. We have a magnetic field, we have a coil placed in a magnetic field. Now we know this magnetic field is produced by field windings supplied by a DC. Now I am showing it's still using a north and south pole. Fine. So once this coil starts rotating in presence of a magnetic field, voltage will be induced in this coil, and voltage will be available along at the terminals. DC voltage will be available at the terminals of the armature winding. Fine. So far so good. This is an open circuit. There is no current actually flowing through this. Only the voltage has been induced by the action of magnetic field on a rotating coil. There is no current as such yet in this net flowing in this circuitry ideally. Fine. Now since we load this, now we'll actually load this machine and apply some out from externally. We'll be applying some load. It can be a resistive load, an inductive load, uh, since we are talking about a DC machine, let's say it's a resistive load. So as the resistance increases, so will the magnitude of current that will now start flowing through this armature also change. Fine. Depending upon the nature of load, depending upon the magnitude of load, armature current will start flowing through these windings, and this armature current will now produce a magnetic field of its own. Fine. So if the main magnetic field was represented by B, the armature current, it's since with since it's an AC current that's actually flowing through the armature windings, this alternating current will produce a magnetic field of its own, and that will be that I am showing here by BA. So what will happen is that this magnetic field that's now being produced by the armature current will actually be in opposition to the main magnetic field that was produced by the field windings. It will therefore influence the main magnetic field. There will be actually again two changes in the main magnetic field. Either it will cancel it out, or it may there will be a cross demagnetizing component, or there can be a cross magnetizing component where it will actually reduce the value of the magnetic field. So this distortion of magnetic field or flux, what you can say, this distortion of main magnetic field or flux, whatever you want to call it, so this distortion of the main magnetic field by the armature magnetic field that is actually produced by the due to the loading effect of the DC machine, this is called as the armature reaction, and so therefore the magnetic field will be reduced, or you can even say it may be demagnetized totally. So this is basically an issue that is associated with DC machines, and there needs to be some mechanism to mitigate this problem, wherein we can actually reduce the effect of armature reaction on the DC machine. Fine. So what happens is, simply stating, as soon as we load a DC generator, armature current will flow. The current will actually flow through the armature windings. Normally also at no load, the armature current is almost zero. It may not be exactly zero because of the internal resistance of the windings and the inductance of the windings, but because of the loading effect, this armature current is uh, significant enough to produce a magnetic field of its own and distort the main magnetic field. So the main magnetic field is therefore reduced, or it is demagnetized, and this problem is known as the armature reaction. We need to see what will be the effect of this armature reaction on the DC machine, as well as we need to understand how to mitigate this problem. Fine. So there are actually two problems, as I said. The first problem that is caused by the armature reaction, two problems caused by armature reaction. One is shifting of the neutral plane. So if we take for example, this is the North Pole, and the South Pole. This is here your North Pole and the South Pole, two-pole DC machine, and the armature with the conductors placed in between. So say for example, initially this machine is unloaded. As the machine is unloaded, you can see a uniform magnetic field is produced, that's emerging from the north and moving to the south. Fine. Now what happens is when we load the system, armature current begins to flow through these conductors. Current begins to flow, and also note that the magnetic neutral plane basically refers to that position wherein the magnetic field is actually parallel to the magnetic. In case of a magnetic neutral plane, it is actually that plane which actually is in parallel to the velocity of the rotor wires. Fine. And in such a case, at this around this plane of axis, the induced EMF is actually 0. So this is referred to as the magnetic neutral plane. Now when we load the armature, that means current begins to flow through the armature conductors. So current will flow through these armature conductors. So once the armature conductors, once the current begins to flow, the armature will produce a magnetic field of its own, and the nature of magnetic field that will be produced will be somewhat like this. The direction of magnetic flux being like this. Right? So this will be at this end. And accordingly at this end. Fine. So initially the pole flux is uniformly distributed, and once the armature is loaded, the current begins to flow. The armature magnetic field will, as shown here, begins to armature flux. This armature magnetic field that will be produced by the armature conductor will actually be concentrated along the armature conductors. That will be given by the right hand thumb rule. So for each conductor it will produce its own magnetic field, and you can actually sum up for different number of conductors, and this will be the total resultant armature magnetic field that will be produced. Now we can see as the direction of current is by the right hand thumb rule also you can get basically if the direction of current is upwards, that means out of the page, the magnetic field will be shown by the curl of the hand. Fine. If the current is in this direction, the magnetic field will swirl along this direction along this conductor. Now since there are a number of conductors placed together, so this will result in a net magnetic field like this. So at this end you can see now the magnetic field produced by the armature is in phase opposition to the main magnetic field, while at this end the magnetic field produced by the armature is in phase with the main magnetic field. Similarly, at this end the main magnetic field and the armature magnetic field are in same phase. At this end they are in phase opposition. So therefore the magnetic field changes like this. Fine. So at this end of the North Pole and at this end of the South Pole, the magnetic lines of forces will be more as compared to these two ends of the North and South Pole. That means the magnetic field will be now concentrated more towards the edge of both North and South, and the magnetic neutral plane therefore will no longer be at this point. It will be in this direction. It will be along now in this direction, at which the induced EMF will now be equal to 0. Fine. So therefore what happens is the neutral magnetic neutral plane, where actually the EMF was supposed to be 0, now gets shifted, and it will be shifted. Now this shift will now depend whether it's a generator or a motor. For a generator, the magnetic neutral plane will be shifted in the same direction as the direction of rotation, while as for generator MNP, that's the magnetic neutral plane, shifts in the direction of rotation. For a motor, what will happen in case of a generator is that at the trailing at these ends, these are actually the starting ends of the poles, the concentration of magnetic field will be more, while as in case of motor at the trailing ends, that is at these points, the magnetic this will be more concentrated, the magnetic field lines. Therefore in that case, in case of a motor, the magnetic neutral plane will shift in the direction opposed to that of the direction of rotation, whereas in case of a generator the magnetic neutral plane shifts in the direction of motion, in the direction of rotation. And the magnitude of this shift will actually depend upon the magnitude of armature current flowing through the armature windings. Fine. So this is one effect of the armature reaction, that is the magnetic neutral plane will be shifted from the from its original position to either in the direction of motion if it were a generator, or in the opposite direction if it were a motor. Now what happens because of this shift in neutral plane? The commutator basically will short out the commutator segments at the moment when the voltage across them is equal to 0. Fine. This is what actually happens whenever the commutator is basically rotating along with the armature, whereas the brushes are stationary. The commutator must always make sure that the commutator segments short at the brushes should be in contact with the brushes. Whenever there is a motion of rotor, whenever there is a motion of commutator segments, let me show you from the diagram. Fine. So say for example in this case the commutator is as well as rotating, but the brushes, they are stationary. So you will see at some position the commutator A and I, if it is rotating in this direction, at the time will come when A and I both will be shorted by the brush segments. So what happens at this time, the voltage actually should be equal to 0, so that there is a smooth commutation between this process is actually known as commutation. There is a smooth commutation between the commutator and the brushes, so and the voltage across them should be equal to 0, so that they are not, there is no sparking or there is no short circuit at that time. But if the brushes are set to short out the conductors, what will happen is that voltage between each segment is indeed actually 0 until the machine is loaded. But once the machine becomes loaded, this magnetic, because of the change in the magnetic neutral plane, we make sure that this basically does not happen anymore. What happens is that at the moment of the brushes were actually first aligned in the magnetic neutral plane so that the EMF induced would be 0. But since the brushes are no longer, since the magnetic neutral plane shifts as soon as the machine is loaded, the brushes are no longer in the magnetic neutral plane. They will be in a certain other direction where the EMF induced would not be 0. Therefore, the end result will be basically arcing or sparking at the brushes. Fine. We place the brushes in the magnetic neutral plane where the EMF induced is 0, so that smooth commutation between commutator segments takes place. That means reversal of current from one commutator segment to another commutator segment. It takes place smoothly without any sparks or any flashovers. But as soon as the neutral plane shifts, once the armature is loaded, the brushes, they are no longer in the neutral plane. The voltage induced in this plane will no longer be 0. So brushes are actually located now in a place where voltage induced is not 0, and therefore sparking or short circuit will take place at the brushes. In extreme cases, there may be a flashover, and that may actually even result in the burning of the motor. So what we can do is we can actually shift the brushes in the direction of in the slide towards, if it is a generator, if it is acting as a generator, we can shift it towards in the direction of rotation. If it is a motor, we'll shift it in the opposite direction to that of the rotation, so that actually it may be in the magnetic neutral plane or close to the magnetic neutral plane, so that this flashover or this sparking problem is basically reduced. So we'll continue discussing about the problems associated with the armature reaction and the commutation in the next session.